Thank you for those who came early. He was right here. What happened to him? Well, why don't we go ahead? I'll give a brief introduction. Um, I hope most of you have met owner Tustan. Dr. Tustan is a geotechnical engineer with CDM Smith with about 10 years of consulting experience on national and international nuclear power plants, dams, water and wastewater, conveyance and treatment systems, and other important structures. His academic experience includes soil liquefaction and geotechnical earthquake engineering. And this particular subject, risk assessment, is one of his favorite topics. I think you'll see that today. Owner has 2 daughters and loves playing and watching soccer. I'm going to guess that his favorite Premier League team is Manchester United.
I don't per se have a favorite,
okay.
But Manchester is not one of my favorites.
Dr. Tustan.
Hello. Thank you, and I hope to not bore you out with this presentation, so I'll promise I'll do my best, and I'll try to make it as interactive as possible so we at least stay awake throughout the whole presentation. So, let me just go in here. The title is Risk-Informed Decision Making, and this term specifically has been used by Army Corps of Engineers and U.S. Bureau of Reclamation, USBR, in the past 10, 15 years. And please note that they're not saying risk-based, it's risk-informed. And that's an important distinction that they make, because they're saying even the risk assessments that we will just explore in a minute are not, even though they may be numbers, are not very comprehensive and thorough in the sense that they shouldn't give false sense of security to the user. So it should be risk-informed, not risk-based. So the first 5 to 10 slides are basically introduction of the terms that are commonly used in the FEMA, USPR, and Army Corps. And the good thing is that these terms are pretty common in all of those references. So once you get familiar with them, you will be able to use any one of those reference documents. And then I will spend some time in basic statistical concepts. I'm sure you've all seen that in the past. So hopefully this will be just a reminder of those little things that could be useful in the risk analysis. And then we'll talk about risk analysis, risk assessment, risk management, and not so much on the risk control side, but I guess you guys are dealing with that right now with one of the dams. So a bunch of references for your use later if you want to go back and read any of these documents. That one? That one is a paper that I published in 2017. A little bit of a history on that. In the nuclear power plant side of the picture, there's a process called probabilistic risk assessment. They refer to it as PRA. And that's a very common thing to do for the existing nuclear power plants. And after post-Fukushima, the disaster in Japan, NRC required all the power plants to do this in a very comprehensive way. But they could not do it in the way that we will describe in the next slides, and they followed simplified procedures to do a very comprehensive PRA. And in that paper, I try to explore if you can use those simplifications in, say, a dam risk assessment. That was, if you say have 50 different failure modes, I'm just exaggerating, you're not going to have that many, but you don't have time to go through a comprehensive risk assessment. Is there easier, shorter ways to get there? So that was the reason for that paper. So, dam safety evaluation. Historically, this has been the practice, standard-based very prescriptive approach. Follow this document, follow these routines. You'll get a factor of safety. You'll get this number. If it's below this, you're good. If it's above this, you're not good. And that kind of an approach. It was mostly deterministic, not much of a probabilistic there. But recently, since I want to say it started around 70s, but the real start date is probably 94 to 99. It starts with Australians leading the way with Ancolt documents, and then 99 there's an Army Corps publication too. So since 90s, I want to say that the risk-based approach has been taking root, and it's been commonly led by Army Corps and USBR. And most recent documents that you will see in the next few slides are jointly published by these two entities. So they're working together. Same thing, starting from 1970s. The process has been changing. And as you very well know, the current practices based on either the loss of life or the dam size, the categorization of the dams. And that process makes no differentiation between loss of one life versus 1,000 life. And it also doesn't take into account, yes, this dam, for example, might be one loss of life, but it's in such a poor shape versus 1,000 lost life, but in such a good shape. So how do you compare the two? There is really not a good way of using these existing procedures and methods to evaluate cases like that. So what they do in the risk-informed decision-making process is to implement a thorough and systematic and rigorous process to assess the dam safety, in which you can come and use this curve. So, speaking of this curve, this is called an FN chart. How many people have seen this before? So, two. That's at the end of this presentation, I just hope that I'll do my best so that you guys will know this very well. So this should be one takeaway from this presentation, that you've seen this and you know what this means. So on the x-axis, we have number of fatalities. This is the most common way of using it, but this x-axis can also be cost. So it doesn't have to be always number of fatalities. But for our purposes, I think it makes sense to keep it this way rather than money. Here, probability per year of potential loss of life. So for a given loss of life, what is the probability for that to happen? So you will see in later slides that there's a capital F and a small f. The capital means considering all the failure modes, all the likelihood of events that leads to this loss of life. The little f will mean for one failure mode. That's the distinction between the two. So here's by the way, this is a book that I really like, and it is, I think, reliability and statistics, or reliability or probability in geotechnical engineering. It's a good book. It's a good reference to have. So you can see the fatalities and frequency here, an economical scale here, annual probability of failure here. So I would like to give you a moment so that you can examine different structures and where they plot in these FN curves. Please notice the dams right here, and you can see this is 10 to the 0 and this is 10 to the minus 6. So it's going this way, it means unlikely to happen. So dam failures are on the more unlikely case scenario, whereas mine pit slopes are more likely to fail. And you can pretty much imagine why that is. They want to take the most out of the mine, and they are willing to take risks for that. So the foundations are here, dams are here, and you can see two lines here. One is called accepted and one is called marginally accepted. So if you calculate your annual probability of failure and the loss associated with it, if it plots right here, what will we say if it plots right there? Not acceptable. And if it plots right here, we're good. So that's the use of these charts. Risk terminology. This is out of the FEMA manual, FEMA 1025, which basically develops the framework for the risk-informed decision-making process. It's called Risk Management Framework. Everything starts with the failure modes identification, or in FERC terminology, PFMA. It goes into risk analysis, and this is where most of the computations or analysis are done. So all the evaluation of the uncertainties in the parameters you use, all the mathematical equations or models or whatever you do, mostly it's done here in this step. Risk estimation and risk analysis. And then when you go to the risk assessment, that's where you look at the results, you look at the criteria, you look at different variables and evaluate the overall risk that you calculated. And now you jump into the risk control. Is there anything you need to do to reduce the risk? Is it necessary to reduce the risk? And if it is necessary to reduce the risk, then you look at the activities that you need to do to reduce that risk. And you keep doing that periodic reassessments, because obviously the conditions change, and that risk might change as well. Okay, here's another important slide. The risk consists of three components: the hazard, performance, and consequence. We multiply these three probabilities, and what this actually means is you have to have a likelihood of hazard, a flood, and there is a probability associated with the likelihood of a design flood. And then, given that flood level, the dam has to fail too. So there is a certain probability for that to happen as well. And then the hazard happens, the dam fails, what's the likelihood for that consequence to happen? So these three components have to come together for you to calculate the risk and then plot that in the FN curve. I'll explain it in a moment why we multiply these three. I explained this one, so I will just skip through risk analysis and risk assessment. This could be quantitative or qualitative, and there are procedures to identify failure modes, events, and the conditions for failure to occur. Risk management is actions implemented to communicate the risks and either accept it as they are without doing anything, avoid them, or transfer or control the risks to an acceptable level. Of course, at the base, on the basis of cost and benefit. Risk communication. FEMA mentions that risk communication has to happen at all steps along here with all the stakeholders involved in the process. So I put two FN charts here. One is from USBR and one from Army Corps, and you will see the similarities in between the two. If you look at it closely, you'll see the numbers are pretty close here, 10 to the minus 6, 10 to the minus 6, 10 to the minus 4 here. And they have different identifications here, and one term, ALARP here, is that how you pronounce it? ALARP? ALARP, yeah. What it means is as low as reasonably practicable. I think that's pretty self-explanatory on what that means. And you look at these terms again, as I mentioned earlier, individual failure mode, and the capital F is the cumulative risk with all the failure modes. And let's read here, risks are unacceptable except in exceptional circumstances, just like I mentioned earlier. If you plot in this zone, risks are unacceptable. As opposed to if you're here, risks are tolerable only if they satisfy ALARP requirements, and they are defined in this manual here. And here, risks may be unacceptable or tolerable, but will be examined thoroughly. Here's an alternative to the FN chart that you've seen earlier. So this is a qualitative analysis. It's a risk matrix, and on the x-axis you have the consequence category, and on the y-axis you have the likelihood of failure. So these can be defined for any application, say for the dams that we have in South Carolina, and we can define these categories in level 1, level 2, level 3, and level 4. And then we can also define the likelihood of failure as well. And all of the dams that we have, say 400 something high hazard dams, can be categorized in one of these little boxes here. And that gives you an access to prioritize your risk reduction measures, or which ones are more important for you. They're all important, obviously, but some of them may require remediation before the others are in that position. Okay, here's the hopefully not so boring part. Basic probability concepts. This terminology is P, in parentheses A, probability of event A occurring. And this little sign here means the mutually exclusive part, or complementary events of the A, which is probability of event A not occurring. They are called mutually exclusive, which means both cannot happen at the same time. You have either the one or the two. An event and its complementary event are collectively exhaustive and covers all possible combinations. This sign here, I'm sure you remember that very well. Events A and B occurring simultaneously, and this sign means it's either event A or event B occurring. When that probability of something, in our case, is always greater than 0. If it is 1, that event is likely to occur. And the complementary of event A is 1 minus probability of complementary of A. So that's simple, I hope. And probability of A or B is equal to probability of A plus probability of B minus probability of A and B. This is really important. This sign means probability of A happening given that B happens. Where is it? Oh, right there. Does it work? Okay, great. So I'm going to have to use both at the same time. Okay. So this one is important. This means probability of A happening when B happens. Like we said earlier, mutually exclusive events, A or B, probability of A plus probability of B, and this one important, probability of A and B is equal to probability of A times probability of B. Let me see what else is the important one here. So here you can kind of deduce this equation yourself too. So probability of B times when B happens, A happening is equal to A and B occurring together. Does that make sense? If you look at it, if you put this term on the other side, probability of B happening, and then when B happens, probability of A happening, which means A and B happening together. I think this is also pretty explanatory. 1 minus no fail is equal to probability of failure. And this equation, if you have, say, 10 different failure modes, and you're looking at overall failure, you have to look at a lot of or statements, right? 1 can happen, or B can happen. 1 and 2 happen, but also 3 can happen. So in order to eliminate all those ors, you can use this kind of equation and get to that by eliminating those ors. Bayes' theorem, I'm going to skip that for now, but it's there for your reference. Okay, the definition of random variable. Has anybody heard of that? Random variable is, the name is fancy, but what it means is when you look at a parameter, you look at it whether it's a constant or it has some uncertainty associated with it. What would be a good example for that? I don't want to say naturally changing condition, but say a crest elevation for a dam. Does it have a lot of uncertainty with it? No. That's what it is. It's not going to change much. But say a friction angle for a material inside the dam, a sandy material, there's a lot of uncertainty associated with it. How do you measure it? How variable it is in the dam? So it's not a constant one number, even though it is reported as one constant number in a lot of the permit applications you will see. So that is essentially a random variable. So in reality, how we should treat it as is, instead of saying friction angle is 30 degrees, it's a number between, say, 25 and 35 degrees. So that means it's a random variable. And that's a fundamental thing for the probability analysis. You start with that. You define parameters that you need, and you define ranges for them. So how do you define those ranges? Instead of just saying it's between 25 and 35, you give it a distribution. And you might remember these distributions from statistic classes from back in the day. But the most common one, in my experience, is a log normal distribution in a lot of the things that we do in our fields. Why? Because log normal distribution doesn't allow negative values. Here's an event tree. I'll try to make this as easy to follow as I can. So a failure mode 1. You go into a node where it's either yes or no. And for this probability of failure mode to not happen, the chance is 90%. For it to happen, the chance is 10%. Say that happens, that failure mode, the first initiating event, in this case it says reservoir reaches this elevation, and that happens. And then you go on, does the concrete crack? Yes, and the event likelihood is 30%. And then when the concrete cracks, does the breach occur? Yes, is another probability of event occurring there. So as you can see, this is chain of events, and you can look at the PFMAs in this regard. So this is just one of the failure modes, and you don't have just one failure mode, you have many of them. So you have this event tree pretty complex. If you have 8 to 10 failure modes, you have to have chain of events that you propagate. And let's see, so at each node, you can see there is a yes or no. And also you have a probability of occurrence. Say we want to get to this number here at the end of this branch here. How do you think we would do that? Remember the first equation that I was talking about? This happens, and then this happens, and then this happens. A chain of events. Remember the first equation, hazard, performance, and consequence. What was the term that what was the process that we followed? We multiply those three, right? Independent. So you can do the same thing here, and you get to a number here. So each of those branches will have that, and then if you want to get the total probability of failure, you add all those branches. This is a yes or no type of a node, and there's also other types of node where there's some logic to it. So there might be more than one way of evaluating that yes or no, and that's a different way of building these trees, and that gets a little bit more complex, so we don't have to talk about that now. So this is just a fancy way of saying what we just said. If you remember from the earlier slides what these means, so this is probability of the event A happening, and then this means A happens, what's the probability of B happening, the second event? And then here, A and B happen, what's the probability that D happens? Okay, so after with that little background on statistics, let's go back to our general framework and start diving into the risk analysis and risk assessment. Risk analysis. We have defined this before, well, let's say it again. This estimates the risk to individuals or populations and properties from the environment, environmental hazards. It involves scope identification, hazard identification, and risk estimation. The risk evaluation is examining and judging the significance of risk. Risk assessment is a decision-making process for deciding whether the risks are tolerable, risk measures are adequate, or you should implement alternative risk measures. It's simply a combination of the risk analysis and risk evaluation. So, how to get that FN curve? If you remember, we said that the first thing is the hazard, the second was the performance, and the third was the consequence. So the first part, the likelihood of exceedance of loading, is the hazard. So here's an example. This is, let's see, this is an earthquake-related input. It's an earthquake type of loading. On the x-axis, you have spectral acceleration, and on the y-axis, probability of being exceeded. So if you look at each one of these spectral accelerations for earthquake excitation, and you evaluate the probability of being exceeded. And you can see that that's also represented as percentiles. So there's a mean value, and then there's a 5th percentile and 95th percentile. So this just defines the variability in it. I will come back to the second step. We just touched to the first one. We're now looking at the third one. I will go back to second because that's a little bit more involved. The magnitude of resulting consequence. So that's where we determine the life loss estimation. And this is the part I'm sure you guys know very well by now with DSSYs and all that stuff. So there are different ways of doing that. And FERC provides guidance in Chapter 22 of their risk-informed decision-making guidelines. And any one of these methods can be used to come up with a life loss estimation. So the second one, probability of inadequate performance. Here's a bit of a flow chart to get to this point. First, we define the risk modes. We come up with the event tree, right? The second is, for each event tree branch, we have to have a way of calculating the probability of failure. That's a mathematical model. And then what are you calculating the probability of failure? What's the limiting condition? What are you trying to get to? Is it a slope stability? Is it a sliding analysis? Is it overtopping? What is it? And if it is one of those, what's the limiting condition? Well, how do you define as failure is another way of putting it. And then we develop the engineering parameters. What are the input parameters for that? And how do we define them? Whether they are deterministic or they are random variables. And if they are random variables, we develop statistical distributions. And then we develop correlations between parameters, if there is any. And then choose the methodology with which we're going to calculate the probability of failure. And then combine all those probability of failure modes. Here's an example from a real application as published by White and Anderson in 2014 USSD conference, Pine Creek Dam. You can see an event tree. All gates operating, no failures, and then if there's failure, dike overtopping, embankment overtopping, conduit piping, and it goes on, and there's a bunch of events happening after that. So this kind of event tree, as far as I know, there are two tools out there that people use. And this particular one was a software called, I think, DAM-RAAE or something like that, which Army Corps used. And then there's another one called Precision Tree. So the reason I'm bringing this up is that all you have to do is to sit down, think, and develop that event tree. And those event trees are useful even if you're not using a probabilistic concept or a probabilistic approach. The event trees are useful because it makes you think that what are the likely events that can happen to this dam? How can it fail? And once you develop that for yourself, you can put in one of those software, and they do the event tree calculations anyway. So here's another example from the book that I was mentioning earlier. You can see a chain of events. The limiting condition. These can be tricky. Let's give an example. Say you have a critical piping connection or conduit, and there can be liquefaction around it. And you calculated the factor of safety, and it's greater than 1. So does that mean it's okay that I accept that as a limiting condition? Not always, because you might have very large deformations around the pipe. Even though the factor of safety is greater than 1, those pipes can still be in danger. So in that case, you should look at a settlement or a deformation criterion. Can calculate the deformations around those pipes due to liquefaction. In another example, you might calculate a factor of safety for a slope. And under a seismic event, an earthquake, it might turn out less than 1. But that doesn't mean that slope is unstable. You can look at the deformations. There are ways to calculate it during a seismic event, and they might be, that term is, means critical components. That slope deformation is not large enough for it to be a concern for you. I'll just go to the next slide. That's even better to explain that subject. The uncertainty. Let's approach this uncertainty term from a parameter that we use. I gave the example of friction angle. I don't know if that term is very familiar to you. You have all heard friction angle, right? That we use it all the time for the slope stability analysis for dams. So let's take the friction angle. There is an uncertainty of that parameter in the field investigation phase. In other words, there is already a variability in the dam material itself. So if you measure at point A versus point B, there will be variability. They're not going to be the exact same value. In addition, whatever test method you're using in the field will introduce variability. If you use method A versus method B, you're going to measure different values. They're not going to be exactly the same. That's all uncertainty, and that's associated with the field investigation phase. Say you choose a certain method, you measured it at a certain spot, but whatever you measured is not directly friction angle. It could be, if you remember the last presentation, blow counts. You did an SPT test, you measured the blow counts, it's not a friction angle. You still have to go from the friction angle, you still have to go from the blow count to the friction angle, and use an equation for that. That introduces another variability. And then you go ahead and put that in a computer model and calculate the slope stability. There you go, another uncertainty. So when you see a factor of safety calculation in the permit application, and where they say the factor of safety for the slope is 1.8, next time you see, you can imagine that all this is involved in that. And that number doesn't tell you a thing about how big the variability is. Okay, so getting a little bit to the examples associated with it. Taylor's expansion is a simple way of calculating the probability of failure that is introduced by Army Corps. It's not Army Corps' method, but Army Corps suggested that it could be used. And Monte Carlo simulation is another one. Here's an example. This is an example, I put that in that paper. It's a dam. It was one of the dams that we looked at back in the time. And there are different materials here, the embankment fill, native soil, and the sill. So we're going to look at the probability of failure for multiple failure modes. And we're going to look at the performance part of it. We're not looking at the hazard. In other words, it's the probability of failure when the hazard happens. So 2 failure modes: downstream slope failure under seismic load, upstream slope failure under seismic loads. Of course, there are a lot more, but for the simple example, let's look at those 2. Taylor's expansion is using a fancy looking equation here. This term is called reliability. And by the way, the reliability is just 1 minus, probability of failure is 1 minus reliability. Those terms can be used interchangeably in the different references that you look at, but they are correlated, so not a big deal if you calculate reliability instead of the probability of failure. It's defined that way, so the fancy term here are actually not that bad because this means just the expected value. In other words, it's the mean. And here is the variability as the standard deviation for the natural logarithm of the factor of safety. How do you do that? So 3 variables are defined as a random variable for that case. Embankment friction angle, native soil friction angle, and the silt friction angle. So the way to do it is, first, you consider the mean value for each of these 3, calculate the factor of safety. And then you keep the mean for these 2 and look at the mean minus standard deviation here. And then again keep the mean, here it is 2, look at the mean plus standard deviation. So essentially we vary this parameter while we are keeping these the same, and we calculate the factor of safety. And now we switch order. So we kept this one the same, and did the same thing for these 2. And then changed this one, kept these 2. So essentially we did 7 analysis for 3 variables. Using those 7 analysis, that Taylor's expansion method allows you to calculate the factor of safety. Does this sound simple? Honestly. You just look at the mean plus standard deviation, mean minus standard deviation, pick one of those values, run the analysis. And I have to remind you that this is a standard practice to do at least this part of it. Everybody's going to do this regardless of what they do, probabilistic, deterministic, or when they submit a permit application to you for a slope stability analysis, they will do this. Everybody will do this. So all this is doing is add 6 more analysis, and time-wise, if this takes, I don't know, if everything is ready, and if you just, matter of a click, you click on it, and you go back, change the parameters, click on it again. So it doesn't take a whole lot of time to get to this number. This number here, this method itself doesn't tell you that. It's because each and every one of those variables you define are already ranges. So it's using those ranges to give you a number. This in itself, just one value. This will give you one value. The way this is working is that it's looking at a factor of safety distribution. Factor of safety itself is a variable in that case. The inputs are variable, output is variable. And it's looking at that factor of safety distribution, and it's calculating a probability of failure based on that distribution. So the probability of failure is one value there. So if the way that slope W does it, for example, we're going to see it in the next slide, is say it runs 1,000 times. And then it counts the times that the factor of safety is above a certain value and below a certain value, and looking at the ratio, it gives you the probability of failure. Does it make sense? You look at the probability of failure. That's one number. Let's go back a few slides. Let's say that this branch represents the slope failure. and you're saying that earthquake hazard happens. We go into this, yes. And then slope failure, 30%. That 30% comes from that particular analysis. Does it make sense? Okay. How many people have seen slope W results in the applications? It's not very common, I guess. Slope W is a very widely used software in geotechnical engineering, in evaluation of upstream or downstream slope stabilities. And in that particular software, they have an option where you can go and choose a probabilistic calculation and define, say, I want to run this model 2,000 times. So what it does is, remember those 3 variables that we were looking at? And we looked at 2 variations for each parameter, right? We looked at the mean, and then we looked at the mean plus standard deviation, mean minus standard deviation. With this method, instead of looking at 3 variations, you look at 2,000 variations. So you're not limited to yourself. You're not limiting yourself in just 3, and you're doing 2,000 times. And the software also, to do that, asks you a range. Okay, I'm going to do this 2,000 times, but I have to choose 2,000 different values. Where do I choose that? And you say, okay, look at this range, and this is totally up to you. You can define a distribution. In this case, it was a normal distribution. It should be log normal. And you can define that range. 3 different properties and 3 ranges. And then it runs 2,000 times. Okay, so for a given earthquake level, say the PGA was 0.2 for any given earthquake, Taylor's expansion and Monte Carlo simulation. So this one is Taylor expansion, this is Monte Carlo for different failure modes. You can see they are tracking pretty closely for different earthquake events. They're not much different. So Taylor's expansion, as proposed by Army Corps, works pretty well. Why is it important that they are close for practical purposes? Remember, Taylor expansion, we did it in a simple spreadsheet, and we run 3 cases. In total, we run 7 cases for 3 different properties. For Monte Carlo, we run it 2,000 times. Why is it important? Time, right? Like, for a seismic analysis of a dam, it's not something that we do often around here, but say it's a very important dam, somebody's doing a numerical modeling and a seismic analysis, and that model can take up to a week to run it. So doing it 7 times versus 2,000 times is a huge difference. In one case, it's time prohibitive. You can't do. So it's important to see this comparison. Okay, so far I hope I haven't lost you guys. So let's see how can these be useful. Some questions. How do you compare high hazard dams? Say you have 400 of them, and you're looking at the 200th dam versus the 300th dam. How do you compare the two? Which one is more critical for you? How do you answer that question? Let's make this part interactive, see if we can get somewhere with it. Right, we get what's wrong with it. Yes, how many people can die? That's one aspect, right? What else? Right now, all we have is a high hazard. We're just saying they're both high hazard, which means people can die. But we're not differentiating how many people can die. So we're not doing that differentiation. Which high hazard dams pose more threat to South Carolina? You could take it as economically, you could take it as loss of life, any way you want. But which one is more critical? A follow-up question, if funding was available today if the state or the federal government gives you $10 million to fix the critical dams, which ones you would choose? Is there a way to establish it right now? It's very subjective, right? Your opinion versus my opinion. So, similar thought process Army Corps went through for their levies. And there was a webinar recently where they've gone through their report, and they have done a risk-based assessment to order their portfolio of levies to determine which ones are needing immediate attention, which ones don't. So here is a action classification table from that document. I provided that reference for you, and I suggest that you guys take a look. It's a good read. It's not that complex, and it provides a good framework. From that, you can see they did the risk assessment, and they come up with the fact that 76 of those levies are in high risk or very high risk categories. So if you want to compare between those 76 itself, you can do more detailed assessments. You can do the quantitative risk assessment. Essentially, what we have shown so far, you can do those to 76, but you cannot do it for all 2,200. Is that making sense? So they started with a more qualitative approach. They developed this, and they're suggesting that you can do the more comprehensive quantitative one on the 76. So the qualitative, going back to this little matrix. So the x-axis, for your specific case, you've done a lot of work already with the DSS-wise runs and potentially GIS-based population maps to come up with a consequence category, right? We can define those consequence categories. The likelihood of failure, low, moderate, high, very high, there are different ways to look at it. See, probability equivalent. For an event virtually impossible, you see the probability equivalent. And in the very end, virtually certain, 99. So, likelihood of failure. So what we could do, for example, is we could look at a certain dam and look at the potential failure modes. Say, let's take the current dam that we're looking at. What's the failure mode for that? How can it fail right now? Piping, right? Any other failure mode that we can think of right now? We can count 2 more maybe, but you're looking at 3 failure modes. So if we sit down and look at each and every one of those failure modes and ask Jill, John, me, Steve, and Pat here our opinions, please tell us, based on the table you see here, what's the probability equivalent for the piping to happen for that dam? Very likely, right? So I'm just saying it, we all can have our opinion, but if you pool our opinions, you may get to a certain probability of failure. Yeah, you can do that. You can do it for an individual. Yeah, you can do it for a higher level, a group of dams, or you can do it even a single dam. So, yes. So, all I'm trying to explain here is that with a sort of a systematic process that is not so quantitative, we can classify our dams into this matrix. And you can plot them in, I don't know, upper right-hand corner or the lower left-hand corner. All 400 high-hazard dams will plot somewhere here. And if it plots right in the upper corner, if you have 10 of those dams and you need to differentiate further to see which one comes first, you can do the quantitative analysis that I've gone through in the slides and go differentiate even further. Does it make sense? So the first step, and then you go to another step. And everything I've said or gone through today might sound complex, but I just want to leave you guys with this, that this has been done. This part has been done a lot more often than the other one, but even the quantitative part has been done in quite a few projects, Army Corps projects primarily. Questions? This is what you're saying. Each one of those, this consequence category, that's how you define it. Level 1, you, you would sit down and decide what that is. Is that 10 people, 100 people, one person? Or on the other axis, likelihood of failure, is there spillway, enough spillway capacity? You send an inspector to the field, and you give him 5 scores in spillway capacity, 1, 2, 3, 5. He goes there, it says it's 3. The other one, it goes 1. And then we plot those here. This has to be drilled down and put a list, and that's what initially is going to take time, to have a list of questions. And each question will have a rating, and then you will have those ratings compiled, and that way it will plot on the y-axis. And it will be very easy once you have that built. For any given dam, it's a matter of answering questions. And a lot of the inspections are already available. As a matter of fact, based on those inspections you have at hand right now, you could probably even do that sitting in the office. And if you can't, if you don't feel comfortable, you can go back and inspect. That's where the event tree comes handy. Yeah. What event tree does is, you build that, like I said, it's a thinking process. 3 people come together, sit down, and develop that event tree. You do it by hand or by software, however you want to do it. And at the end of the day, when you calculate your probability of failure, again, those probability of failure, say you don't do calculations, you just throw in numbers that you think is appropriate. So I think that's 10%. It's just my opinion. I don't want to calculate, it's just 10%. That program will tell you which one of those event tree branches governs. In your case, if you say spillway, it will tell you spillway probability governs everything here. And then you go back and address that further. That's where they find it useful. They used to do this for the nuclear power plants. So they look at core damage frequency. They have, I don't know, thousands of event tree branches. And the statistics expert go back and tell you branch number blah blah governs the whole thing. That's where we have to spend our money. It's I know it sounds a little bit intimidating. I admit. I've gone through that myself too. Um, it still has its challenges for me too, but I believe it's useful, especially this part is useful for classification purposes. Any other questions? Exactly. A lot of the dams overtopping and piping, those are pretty common ones, and you can just sit down and there's what Steve was saying, expert opinion elicitation. There's a whole theory behind it on how you can ask opinions of 5 people and how by doing that you really converge to the right answer. Yes, I know that if I say my opinion, like you said, I'm just pulling it up from the air. But if you ask 5 people, that kind of tends to converge.
Last part was a grammar.
Hmm?